So last time we started doing topological superconductors, and we got to showing that there is a class through an explicit example, but also through some general thoughts, that there's a class of superconductors which is topological in the sense that A is not adiabatical continuable to the atomic limit, and B exhibits Majorana modes at the end of a one-dimensional sample. So today, and we gave an index for them. We gave a 1D non-interacting index, which is this Pfaffian index, and we gave a interacting index, which is this Z2 anomaly that appears when you thread flux to the system. So now, what I want to do really quickly is I want to do an example of an SPT phase with a bunch of these chains, and then quickly move to 2D and hopefully get to, over the 1 hour and a half, to defining fusion rules for vortices and non-abelian statistics, and then continue more generically, or more generally, tomorrow. Okay, so let's take one of these wires, the Hamiltonian of which is irrelevant, but it's in a topological phase, and it's got a Majorana mode at one end. I'm just going to focus on this end. So just think of it as semi-infinite. So this is topologically non-trivial, and this is gamma 1. And now take another wire. In fact, you don't need to take multiple wires, but it's effectively a multiple wire model. You can build one model in just one wire with multiple Majoranas, as Felix pointed out. Take another wire. It's got another Majorana gamma 2. So take however many wires you want, a number Z of wires you want, and put them on top of each other. And they're all topological when they're far away. Now you bring them close to each other. What's going to happen to these Majoranas? Well, they're going to hybridize. And in single particle, so non-interacting, if I focus at the low energy behavior, so close to zero energy, so each of these wires has a superconducting gap that we assume for the purposes of today's lecture to be infinite, okay, or large. But it's got like a Majorana mode here. I'm not plotting the one on the other one. And then you've got another Majorana mode. They're all close to zero when they're far away. All Z modes. And now you bring them close together. What's the only term I can write down in single particle that will couple these Majoranas? So I have Majorana gamma I, or gamma J, and the Majorana gamma K. So what operator do I need to introduce between them to write a term that couples them and splits them? Ah, come on. Everybody had a nice nap on the operator is the one that, well, you just inch this closer. It's a multiplication, okay? Okay? And what do I need to put in front to make hermetic? Okay? And now I'm going to sum over J and K. Is it clear that this is the only single particle term that I can write down? Okay, and I could put different hybridization between them, but I choose to keep this hybridization at the same value equal to 1 in some units. Okay, so obviously this, if there's an even number of them, this is, you can think of it as, let's put some matrix here. If this matrix is antisymmetric, obviously it's got some details, microscopic details of hybridization. If the number of fermions is odd, what will happen? I diagonalize this matrix. An antisymmetric matrix that's odd has how many generically zero eigenvalues? 1. So obviously the Z2 character of the state still remains. If I have an odd number of Majoranas, an even number of them will hybridize, move away, one of them will stay at 0. But generically, that's all I've got. So now what I want to do is I want to forbid such a term. So that's the kind of like, constructing an SPT phase by hand. You want to forbid such term. And what operator, invariance under what operator, so this is the low energy Hamiltonian. What operator do I need to require, what symmetry do I need to require in order to kill this term? It's got an I in front, so what symmetry? So spinless time reversal, which is K, times some matrix, some unitary matrix, that so times some unitary matrix, time reversal, spinless time reversal. So this is matrix is symmetric if it's if you've got t squared equals to 1, and anti-symmetric if you've got t equals to minus 1. So generically, in some basis, time reversal is going to look like this, but I can generically put a matrix here, M, and then you can prove a theorem that if you require invariance under this, then trace of M eigenvalues are going to remain at 0. So generically, not all of them are going to remain at 0. Depending on the representation, trace of M of them are going to remain to 0. But in any case, if I do this, the matrix here is 1. So all of them will remain to 0. And that's obvious because, right, if this K sends I to minus I, so this Hamiltonian is not allowed. So with this operator, you get a Z classification. Okay, because I can bring these Majoranas together, and they won't split up. And I don't care what the bulk does, as long as the bulk is time reversal invariant. Okay. By the way, it doesn't need to be a model that is so contrived, such as spinless fermions with spinless time reversal. You can have models. You can have symmetries that square to 1 that are still anti-unitary. That combine spatial symmetries and time reversal. So for example, spinful time reversal. So for example, in a realistic model where I have both mirror symmetry and time reversal, with spin time reversal squares to minus 1, mirror squares to also minus 1, because you also flip the spin. Okay? So if I have a combined magnetic symmetry, call it TM, mirror times time reversal, so not each of them is broken, but I have this combined symmetry. This symmetry, first of all, is anti-unitary, because this is unitary. This has got a K, a complex conjugation. Okay, and it squares to 1. Tm squared is equal to minus 1 times minus 1, 1. Why? Because time reversal commutes with any spatial symmetry in your system. Is that clear? So, yeah?
Okay. What was the property used? You said that if it's an antisymmetric matrix, it has to have 0 eigenvalue. If that term isn't excluded.
Yeah, I can send you to the paper that you can prove this. I mean, it's an appendix.
Can you just state the property?
It's the property that it will anti-commute with a Hamiltonian. The actual matrix in front of it. I don't have time to go through it, but the property is that this matrix will anti-commute with this because this K, this full matrix commutes with it, and this K anti-commutes with I. So the full matrix will anti-commute with this matrix that you might have here. That's the property that you use. But although it's a simple proof, it requires about a page, so I don't have time to go through it. Okay. So with either this symmetry or this symmetry, the classification is Z. And now what you ask is what happens when I add in interactions. And by default, this is a many-body question because I've added interactions. So what we need to do is look at many-body states. So if I have here Z Majoranas, a number, what's the degeneracy of the ground state that I would get, okay, just from this edge? Let's say Z is even, because if it's odd, I'm screwed. So let's say Z is even. Right? If it's odd, I need to introduce the other side of the sample to obtain a... Let's see Z is even. How many fermions can I make? How many complex fermions? Guys, we need to wake up. Because if the solitude of this place doesn't kill me, this attitude will. So let's wake up. How many complex fermions will I have if I have Z, which is even? How many complex fermions can I make out of Z, even Z Majorana? Z over 2. How many? Each of those has 2 states. What's the degeneracy? So 2 to the z over 2 is the many-body degeneracy. Okay? So normally, how would the many-body spectrum look? Well, the many-body spectrum, it's going to be some rearrangement of the single particle spectrum, but if all the properties are maintained of the non-interacting spectrum, then the many-body spectrum, you fill these. These cost you 0 energy to put in, so you're going to have 2 to the z over 2 degeneracy here, because you can just fill these up, these fermions, the complex fermions that you build out of these. Then you're going to get a gap filling the next level. Then you're going to get a full spectrum, which is like some very dense many-body spectrum. And then, so you're in this ground state. So you think so you're in these two ground states. But then the higher part of the spectrum is just the complex conjugate of this. Is when you fill this up, and filling this up, and filling these, there's the same energy. So you get this. This is how the many-body spectrum will look. Okay? This you have a high degeneracy if you just diagonalize it on a matrix, on a Hamiltonian. Okay? So this is non-interacting. The non-interacting, so if I just fill up levels. So now let me add interactions. And the name of the game is that I'm going to add interactions until I break this degeneracy to 1. Why? Because if I break this degeneracy to 1, then that basically means I have no degree of freedom on the edge. It means I had the bulk, which was periodic boundary conditions. I cut the bulk. The bulk had one degenerate ground state because it was just filling up something. I cut the bulk and I get no other degeneracy. So I have no more edge states. It's the same thing. So basically this is kind of like the ideology of this is that if you find an interaction that gaps the edges, the bulk is also trivial. That's not true in general. For example, fractional quantum spin Hall insulators or many other models, you can gap the edge, but the bulk will still remain non-trivial. But in these cases, it's true. Okay, so the simplest interaction. So I'm going to add sequentially Majoranas and see if I can gap them. So obviously, if I add 2 Majoranas, I can't gap them because this is disallowed by time reversal. But if I add 4 Majoranas, then now I can write a 4-body Majorana term. Okay, so 4 Majoranas interacting term, and this does it need to have an I in front or not? This doesn't need to have an I in front, so this is perfectly time reversal invariant. And the question is, so you've got like some coefficient here of the interaction. The question is, will this gap the edge or not? So how do you do this? Well, it's very easy. You have to just find a Hilbert space in which you can diagonalize this Hamiltonian. This is, by the way, the only interaction that I can write down for 4 Majoranas. Is that clear? Is that? Okay. So I just build 2 fermions out of it. C1, which is equal to gamma 1 plus I gamma 2 over 2, and C2 is equal to gamma 3 plus I gamma 4 over 2. Okay? So I'm building these fermions, and there's only one thing that this term can be. You can actually compute what it is, but there's only one thing it can be. And can you tell me what it is in terms of these fermions? Anybody has a guess? So the spectrum will maintain the full many-body spectrum like this, will maintain particle-Hall conjugacy. It's just that you're sitting in the ground state here. But the full many-body spectrum will still have this single particle. This is many-body. Even though you're working here, you're just working here. I'm neglecting all of these. I'm just working in this subspace, coupling these. It will maintain, it's got to have energies at plus and minus. What are the eigenvalues of this? How many states can I make? What's my Hilbert space? Sorry? So my Hilbert space is 0, 0, 1, 0, 0, 1, 1, 1. So occupy, don't occupy, etc. Okay? which states are degenerate? What is the energy of these, and what's the energy of these? Do we agree? Yeah? Okay. So now you've seen quite clearly that this interaction cannot give me a singly degenerate ground state. Right? So whatever this alpha is, whether it's positive or negative, so whether I add the interaction with a plus or a minus, I always have a doubly degenerate state. Okay? So this is not a trivial system. It still has degeneracy which comes from the edge. Okay? So now if I add, you can go through this example and add 6 Majoranas, but let me add another 4 Majoranas. And that's the reason that the thought process is I've got 4 Majoranas, I remain with a doublet. I'm going to add another 4 Majoranas, split them the same way, make another doublet. Now these doublets I can make Pauli matrices, so spin Pauli matrices out of these doublets and couple them through an S.S interaction. And this can make me a singlet and a triplet. And that's how I get to a singly degenerate ground state. Does that make sense? Okay, so I don't need to write it down. I basically told you what it is. But it's, if you want to write it down, you add 8 Majoranas. The first interaction is alpha, gamma 1, gamma 2, gamma 3, gamma 4, plus alpha, gamma 5, gamma 6, gamma 7, gamma 8. Okay? Now I make 2 doublets out of this one. I'm just looking at, say, whichever ones you want. The ones at minus alpha over 4, if alpha is positive. 2 doublets out of this one. Now I make the S.S interaction in between these. Right? I put a Pauli matrix into these 2 doublets. This times Pauli times this, and this times Pauli times this. This interaction, it's an 8 fermion. It's a 4 fermion interaction for if you write it down in terms of Majoranas. It couples these ones and these ones, obviously. And I put it with a very small beta, where beta is much less than alpha. So now I can work in this Hilbert space. So basically I've done some separation of scales because I don't want to work with the full Hilbert spaces. So what I've done is I first took out the gap, worked only in this one, created doublets in this one. Now I'm going to focus on this lower one. By making this much smaller than this, I can just focus on those states. And this one, you know that this breaks a 2 times 2 into a 1 plus 3, a singlet plus a triplet. And depending on the coefficient in front here, and depending on this coefficient, you can make this the lowest energy. Okay? So there, 8 Majoranas have gone to, upon the addition of interactions, have gone from having 2 to the 4 degeneracy in the non-interacting limit to having 1-fold degeneracy in the interacting limit. Okay? So basically you then argue that if I got rid of the edge states, I've got rid of every topological thing that I have. Again, this is not true generically, but in this case it is. And that's it. A real proof would make me, well, it would make a real proof was given by Kitaev and Fitkowski. They actually build a bulk Hamiltonian that they connect. But you can make this argument from the edge, and for these 1D cases it works fine. Okay, so any questions before I move to 2D?
Is that the simplest way to do this?
Well, it's the simplest way that I know. I mean, yeah, it's the simplest way that I know. And of course, it's actually like, you can generalize this to what I think Frank is going to talk about. you can generalize this to AKLT states. You can add, you can ask, can I add spins just on the edge, couple it to the spin of the AKLT state on the edge, and get, singlets. Basically, the name of the game is being able to get singlets. Okay, so that's for example, that's why the SU2 AKLT chain is trivial, but the SO3 AKLT chain is not trivial. If SU2 AKLT chain lets you put spin 1/2, okay, on the edge, which already has a spin 1/2, and 1/2 like an impurity because it's SU2. When 1/2 times 1/2 can, it's 2 times 2, a doublet times a doublet, goes into 1 plus 3. And that 1 is the singly degenerate state, so you lost the degeneracy. But now, if you have an SO3 AKLT chain and you just add spin 1, so I'm only allowed to add spin 1 impurities. I added on the edge, spin 1 times spin 1/2, if you do the decomposition, will never have a singlet in the spectrum. Okay? And that's basically the same statement that, spin 1/2 is the projective representation of SO3. Okay, let's go to 2D because that's where I want to. So everybody remembers what Joel was talking about, right? Who is Joel? Is this quality mountain air? Okay, so as far as I know, and I wasn't here, but my spies were telling me that he talked about Chern numbers, right? Okay, so what I want to do is I want to now go to 2 dimensions and build you a topological superconductor in 2 dimensions, the simplest one. And this is the P plus IP superconductor. So I'm just going to write down a model. But obviously, as also Ashwin pointed out, these states have a Z classification and they have a Z edge classification. So I will talk about that in a second. So they do exist. So let's just write down a model for them. And again, don't get stuck with models, but that's easy to write. So here I have a kinetic energy. And then I'm just putting this aside just to coincide with what I wrote in the notes, which hopefully you'll get when I leave. Well, of course, you can just take the I out. And there's a star here, but we can make it real. Okay. And this guy, epsilon of P, looks like P squared over 2m minus the chemical potential. It's very similar to what Felix was talking about, except I've now introduced a second dimension. Well, this is not P, this is K. Let's just stick with. So this is kx squared plus ky squared. So can anybody tell me when this would be topological? Hmm? Okay, but more. Yeah, so for what values of mu would it be topological?
They have to be smaller than. It needs to change sign.
Yeah, so what values of mu is that?
You tell me.
Huh?
You're closer to the black hole.
Okay, well, all right. So it's positive values of mu here, okay? So what I want to do, however, is, so what's the Chern number of this Hamiltonian? What would be the Chern number? Anybody remembers what a Chern number is? There the Hamiltonian has a gap. It's got this, I'm just looking at the first quantized Hamiltonian, right? That's the matrix. It's got some energy levels, it's got a gap. You can write a projector into those levels and you can compute a Chern number, and what is it? Okay, so that's good. So the Chern number is really either plus or minus 1, depending on what I've done here. But it's 1. And And I'm going to write a lattice realization of this model in the following way. I'm just going to discretize these things. I'm just going to put them on the lattice. And here, let me just write down in matrix notation. Notice that when k is small, then this reduces to that. Okay? So that's clear, right? That when k is small, this reduces to this. All right. So I claim that here, when mu is less than 0, the system, and mu greater than 4, the system is trivial. And this is just when mu is outside the bandwidth of the system. And in between, the system's got some Chern numbers. Of course, if it's got to have more than one phase, even in between, because you can't go from trivial to trivial and have a Chern number. So it's going to have a Chern number 1, then it's going to go to -1, and then it's going to go to 0. Okay? So let's just, so mu for 0 less than mu less than 2, it's got Chern number 1, and for 2 less than mu less than 2 greater than mu less than 4, it's got Chern number -1. Yeah.
Even if k is smaller, I don't understand how the beta star disappears.
Yeah, because I made it real. That's how usually things disappear. I'm a star kleptomaniac. Okay, sorry.
Mu is in units of delta, or?
Mu is in units of 1. It's in units. It's in units of t. It's in units of 1 over m. Okay, it's in units of. Yeah, so here I should have a t, but that's 1. Okay.
Tau z is the same basis as sigma y.
These are the same basis. Yeah. Look, if I make this real, that's kx times sigma y. Of course, tau.
Yeah, okay.
When things spontaneously appear on the blackboard, just assume the worst. Okay. All right. So now, even without knowing any Chern numbers and everything, it's very easy to show that this has a Chern number. So let's just look in a cylinder geometry. And this cylinder geometry this is x, and this is y. So I make my sample like this, right? If I look in the cylinder geometry, this is a good quantum number. So I can plot my states, my energy, versus ky. Okay? So if I plot them versus ky, then I'm going to focus on 2 different momentas. Ky equals to 0 and ky equals to pi. Now look at this Hamiltonian. This Hamiltonian with periodic boundary conditions in both directions. But I'm going to look at the Hamiltonian at ky equals to 0, and the matrix becomes,
You say that the equation is okay when you look at small k, but if you want to compute a Chern number, you have to look at every k. So what can this?
That's right. So that's why, you have to, there's basically a lattice regularization. You have to do a lattice regularization. That's why, that's why when you find topological insulators, you only look at how the system evolves from the atomic limit. So you can do 2 things. You either know the full lattice regularization of your material or whatever. So supposedly this is a real material. So you look at your somehow you've got all the details of the lattice, and you can just compute Chern numbers. Or you can look at the way the system follows from the atomic limit. And if it crosses, if it's got like a band transition, then the topological class changes.
But somehow here it's completely changed the physics now because.
Yeah, but let's just not focus on that. It's just it hasn't changed the physics. This has the same. This has. It changed the physics in terms that it's got more phases, but this also changes sign between. You can think of k in this regime. you can think of kx equals to pi being k equals to infinity here. Okay? So let's just not get hung up on that. Because, I can make other lattice regularizations. The point is I can always find a model that's got a lattice regularization that's going to have a Chern number. Okay. Good. Okay. So then look at how it looks at ky equals to 0. The way it looks at ky equals to 0 is what? Is minus mu minus kx squared plus ky squared. Did I mess it up, actually? Okay, plus kx plus whatever, ky delta at small ky, right? So I'm going to look, sorry, plus so at ky equals to 0, it looks like this. It's 1 minus mu minus cosine of kx tau z plus delta sine of kx. And at ky equals to pi is 3 minus mu minus cosine of kx tau z plus delta sine of kx. Now you can clearly see that if mu is in between 0 and 2, okay, 1 minus mu is positive, while 3 minus mu is 1 minus mu is negative, while 3 minus mu is positive. Okay? Sorry. Let's just do this. 2 minus k plus kx squared. I'm just making a small kx approximation. Okay? What's that? Over 2. Yeah, make it sine of k. I'm just trying to make the contact with the Kitaev model. Okay, make it k. So you can clearly see that the system, okay, when mu is between 0 and 2, and this was explained in Felix's talk, the system as a function of kx, so at ky equals 0 or ky equals to pi, as a function of kx, either winds or doesn't wind, right? Remember, Felix was pointing out that this term winds? Yeah? Well, I'm just trying to show that this system is going to have a Majorana at kx equals to ky equals to 0, and no Majoranas at ky equals to pi. Okay? So, as a function of ky, at a certain ky, this is a 1D model as a function of kx, right? So I can plot the spectrum as a function of ky on the edge, and I ask, say I'm looking at ky equals to 0. I can rewrite this Hamiltonian, and it's a 1D model now, just as a function of kx. So I can ask, has it got Majoranas in it or not, as a 1D model from what we've learned in the previous lecture. Yeah? And I can write it down at ky and ask, has it got Majoranas there? Yeah? So you can clearly see that at ky equals 0 and ky equals pi, if I do like a small approximation as a function of kx, this winds, but this doesn't wind if mu is less than 2 and greater than 0, right? So this won't have Majoranas, this will have Majoranas. So the spectrum will look like this. You've got a gap, which is delta, and, it disperses. But here, you'll have a Majorana mode, and here you won't. Yeah? Is that clear? But how can that be? Obviously, the spectrum is continuous as a function of ky when I go thermodynamic limit. Well, I can't just have one Majorana here. I have a bunch of states here, and I have a chiral mode, because I have nothing here, but I have something here. Okay, so I have a bunch of states. And this is the chiral mode of the topological superconductor. Okay? Is that clear?
And there's no counter moving maybe?
Well, there's counter-propagating on the other edge.
Yeah.
Okay? Is that absolutely clear? Okay. All right. So now, this is also obvious, if you just think of, I'm not going to go through it because I'll run out of time, but if you think of the edge of the system, if I take a quantum Hall effect and separate, a quantum Hall effect I can separate into kind of two decoupled chiral superconductors, and each of them will have chiral Majorana modes, and that's just basically decoupling a 1D on the edge, decoupling a 1D chiral fermion into two 1D chiral Majoranas. So, for example, can somebody tell me if I write down the operator that creates one state here at momentum k, so say this is ky, and write down the operator gamma of ky, what's the Hamiltonian on the edge? What is the Hamiltonian? Well, far away from the gap when this is just linear. What's the Hamiltonian there? So it's chiral, so it's going to have ky in it. And now what's the sum over ky? And what operators do I put in here? Gamma ky and what? Gamma minus ky. So obviously gamma is equal to gamma dagger in real space. So that means that gamma of k is equal to, when you take the dagger of gamma of k, you get to gamma of minus k.
Should it merge into bulk of
Where it merges into the bulk is a question of microscopics. It will merge into the bulk tangentially at some. It will merge with the bulk bands like this at some ky, but it's a question of microscopics. You can make any of them any, right? Okay, so basically, let me convince you that if I add two of these, I get a quantum Hall effect. So if you add two of these, so if I add sum over ky, gamma ky, gamma 1 minus ky, plus gamma 2, ky, gamma 2 minus ky. This is the same thing as sum over ky, eta, ky dagger, eta ky, where eta ky is I is gamma 1 ky plus I gamma 2 ky. Okay? Now this is a complex fermion. It's a chiral fermion, right? And this is just the edge of a quantum Hall effect. Describes the edge of a quantum Hall effect, right? So who taught you quantum Hall effect here? Somebody taught you quantum Hall effect, right? Or people knew it from before. But everybody's familiar with the quantum Hall effect? Okay. So obviously now I can have a bunch of quantum Hall effect. Everybody knows is described by a Z-class. I can get a bunch of these modes. And I can decouple them. And the same way I can get a bunch of chiral Majoranas. Right? So the chiral Majoranas move like this. Right? So the classification, the edge classification, is Z. The number of chiral modes on the edge is Z. And I won't go through it now, but this is related to the thermal Hall conductivity of the system. Now, what's the difference between a superconductor and a quantum Hall state? Well, in this one particle case, the quantum Hall state, I can describe if I didn't know my spinner here, this would be a Dirac fermion. This would be a perfectly well-defined insulator as a first quantized matrix, and there would be no difference, you know. But since I have the spinner here, the only thing that I can't do is I can't identify the Chern number with the Hall conductance. The current is not conserved anymore in a superconductor, and the Chern number is not identified with Hall conductance. But it still has, you know, the property of being a topological invariant of the projector into the lower Bogoliubov bands. Okay. So now we've established that the edge classification is given by an integer. So edge classification really means is there an observable on the edge that I can measure that will give me an integer that's characteristic to the state. And that's a Z classification, which is the Chern number, which is really related to the thermal Hall conductance. Okay? All right. So now let's see. So that's one classification, and it's also in the non-interacting case. It's also the same as the Chern number of the non-interacting bands. So now let's find out another classification Okay? By asking what vortices do in the system. So is this clear? Any questions?
I have a question.
Yeah.
So if I understand the logic of your presentation, at the beginning you were looking at the one-dimensional system with those minor modes, right? And you said that there was a declassification, and if you had hypersymmetry...
This is the 1D system, yeah.
For the 1D, and then you run from BD1. And then you said that if you do interactions, Z goes to Z8.
Yeah.
Sketch why it goes like that.
I mean, it's more or less a proof, not...
Yeah, it was an argument. It was an intuition why it would happen like that.
Well, yeah, I mean...
Would it be the same thing in 2D there?
Oh, yeah, I mean, since these are chiral, you basically, like, I can't repeat it through an interacting, you can actually, bosonize them and see that doesn't happen. But, it's much more complicated. So I can't repeat it on the board now.
No, it doesn't work. So
No, it will work. You can't gap.
In 1D, you were able to gap out.
That's right.
You went from Z to Z8.
That's right.
So I'm asking what breaks down, why this argument not...
Well, because here I basically, here I kind of have, what really breaks down is some sort of a gravitational anomaly, really. So you've got what you've got is again, by the end of my lectures, if you measure things in the bulk, there's still a mod 8 classification. It's not integer in the bulk. So there's still a mod 8 classification. So I'll go through that in a little. I'll go through that hopefully next 2 lectures. Okay. So somehow the bulk still knows about the mod 8 classification, but this is a chiral theory on the edge. So you're basically just you have a bunch of propagating channels, and if you add any bosonization term, you can't gap them because they're chiral. It's just the same thing as gapping chiral fermions.
The equivalent to the split that you had at 0 volt is now you shift the modes in K-space, so you still have as many propagating modes, it's just that where they cross the zero energy changes.
Yeah, but I could think of coupling them, having a, the momentum doesn't really matter. I could think of adding disorder or anything. And this still wouldn't, the thermal Hall conductance would still be CT squared over 12. So, it would have times pi. So even if, there's no way to basically gap the chiral mode. So the central charge of a chiral conformal field theory on the edge is invariant. You can change a lot of other things in the bulk, as I'll show, but this one you can't. Okay. So it's all right. So now let's do the defect classification. So by defects, what I mean is vortices, and Felix showed basically roughly what I mean by vortices. The vortex is something that winds the phase of the superconducting order parameter by 2 pi. So why is that non-trivial? Well, the reason why it's non-trivial is because the charge, the condensate charge in the bulk is 2e. Right? So actually, if I have any momentum of any electron moving around, that changes the boundary conditions, right, from periodic to antiperiodic. So vortex 2 pi, it's in units of h over 2e. So it's really pi in terms of like an electron momentum. So that's non-trivial. And that's what happens, that's what you saw in Felix's talk. Basically, those operators came with the phase of the superconducting order parameter over 2. Right? So if you make 2 pi, then that operator changes to minus itself, right? So any vortex comes with a line. Any vortex in the system comes with a line along which the order parameter changes by 2 pi. And that's not a trivial change. Okay? That's a gauge choice, but that's a branch cut around which the order parameter changes by 2 pi. So now let me put a vortex in a superconductor and ask what happens to it. And I'm going to put it in a superconductor of Chern number C. First, let's put in a superconductor of Chern number 1, so just P plus IP superconductor. And let me draw several geometries. First geometry being a disk of this superconductor with no vortex. Second geometry being a cylinder of this superconductor with no vortex. Third geometry being a disk of this superconductor, of this P plus IP superconductor, but now with a vortex in. Okay? So this is a P plus IP superconductor. So what has it got on the edge? I don't know if people are not talking because they're bored or because I can't imagine this. What's that? Really? Is that? Well, don't be. What is it? The line between evil and good doesn't pass through nations, pass through human heart. So what's going on at the edge here? If it's a Chern number 1, it's got a chiral mode, so I'm going to plot it versus the momentum on this edge. Okay, I'm going to plot the dispersion. So there's some spectrum with some gap. Okay, and since there's only one edge in this case, I'm going to plot dispersion, but I'm going to plot it as discrete levels in units of 2 pi over n, where n says the number of sites of this system. So now the question is, what happens at ky equals to 0, for example? The spectrum is particle Hall symmetric, so for everything here, there's something here. So so what happens as I get closer to here? Can I have a state here? Why?
Doesn't it depend on whether K is or odd?
So that's what we're asking, basically. That's how we're going to determine what boundary conditions the system has when it's free, when it doesn't have any vortex in. So that's a very good point. So it's both the correct answer and a very good point. So why can't I have one here, one mode here? Exactly at 0. So this level spacing is some velocity times 2 pi over this length. Of course, it goes to 0 in the thermodynamic limit, but I'm making exact statements. So can I have an exact 0 energy state, not power loss split? Why? Now, if it had periodic boundary conditions, there would be momentum would be 2 pi over L or over n times I. So I equals 0 would exist as a momentum.
You need two states because you need to map one to the other, but you only have one boundary.
Well, that's one way of putting it, yes. So that's one way so it's exactly the same as we talked in the last lecture. The spectrum is, a BDG Hamiltonian, if you're solving any Hamiltonian, is an even matrix. Okay? If I had a state here, I would have an odd matrix. So that's the same thing, basically. Right? Okay, so I can't have anything here. So I can't have this momentum. So what are the boundary conditions here? We agree? These don't have a k equals to 0. Okay. Here, can I have states at k equals to 0? Yes, because I can have two edges. And in fact, they're not going to be exactly at 0. They're going to be exponentially split between the edges, but there's a difference between exponential splitting and this power law splitting that's on the same edge. Yeah? All right, so let's see what happens here. So here, I've introduced a vortex in the system. This vortex, what does it do? Since it's a vortex 2 pi, but in units of 2e, so it's really a vortex pi. What does it do to the boundary conditions of this guy?
Is it like a natural gas? I've never seen this before.
Yeah, you can, but yeah, let's think of it as magnetic flux. So what does it do to the boundary conditions? Okay, so this k now becomes 2 pi over n times I. So now, since I know I have a chiral mode on the edge, I do have a 0 energy because I have that momentum. Okay, so this one is on the edge. But I know my system I'm diagonalizing an even dimensional system. So I know I must have even number of states, of single particle states. So this can't be true unless there's another state somewhere else. And that state is the state localized on the vortex. Because the only difference between this and this is the fact that I've added a vortex. Okay? So through this simple argument that I don't, I would say it's a proof, you know that vortices trap Majorana fermions in Chern number 1 superconductors, or -1. Now what happens if I put in a Chern number C superconductor? So not 1, but 2. How many Majoranas would the vortex trap if Chern number was 2? Huh?
0.
Why?
Because there can be 2 on the edge.
So the same argument doesn't apply, okay? Because then you can have 2 edge states. I can move this edge state here, and I can make another one here, okay? And also the simpler way of realizing it is, let me now say, if I had the same argument and I kind of like ran myself around and convinced myself that it traps 2 fermions, then immediately the moment the vortex traps 2 fermions, I could just add a gamma 1, gamma 2 term in the core of the vortex, and they would split. Okay? Is that absolutely clear? All right. So for a Chern number C, how many fermions how many Majorana fermions have you got in the core of vortex? C mod 2. Okay? So the edge classification was Z. The defect classification is Z2. And the index is C mod 2.
What kind of terms would create such a vortex?
Just any what kind of terms would create such a vortex? Like, the superconductor creates vortices by itself because it likes to expel magnetic field, it likes to concentrate it in. So you just put magnetic field in the superconductor and it does this by itself. So Okay. All right. So now, what I want to understand is something else. Also about these vortices. So from now on, everything will be about these vortices. Now let's see, if I add another vortex here, so I add 2 vortices rather than 1 vortex in a Chern number odd. So from now on, I'm going to be talking about Chern number odd superconductors. So I have a vortex in the core. If I add a Chern number odd, if I add another vortex here, will this vortex have a Majorana mode or not? If I had 2 vortices in a Chern number odd.
No.
Why? If they're far away from each other, why wouldn't they have a Majorana mode? So one of them, so I take one. I took one vortex. I change boundary conditions on the edge from antiperiodic to periodic. I have a Majorana vortex. I have a Majorana zero mode here. Imagine a huge sample. I take another vortex. I bring it into. Imagine a thought experiment in which I take vortices and bring them into the sample. Now I change the boundary conditions from periodic back to antiperiodic. Okay? But I have one zero mode in this core of the vortex. So if this vortex doesn't have a zero mode, I'm back to odd Hilbert space. And that's not possible. So this vortex will also get a zero mode. And you have to, obviously it would get a zero mode just by locality. The fact that if this vortex is away, what happens when I bring this vortex in is going to be the same as what happened when I brought the first one in. Agreed? So these are going to have vortices if they're separated. Zero modes. So the core of the vortex, in the core of the vortex, you might have some in-gap states. This might be the superconducting. You might have some in-gap states, but with Chern number odd, you'll have one zero mode, one exact zero energy, and that's a Majorana, because it's a zero energy, and it's one. Okay, so I have 2 of them. What happens when I bring them close? If they're far away, there is zero energy. What happens when I bring them close together?
Wait a second. So now the spectrum for the whole, what happens to the spectrum for the whole sample when you bring the second one in?
It changes to it changes to periodic, to antiperiodic. It changes to the first one. Because if I'm surrounding two vortices, but by just the concept of locality, what happens to the second vortex must be the same. Okay? All right. So now, what happens when I bring these vortices close together? So let's call this Majorana gamma 1. Let's call this Majorana gamma 2. They split. And in fact, let's not call these Majorana gamma. Let's call them sigmas. Just because I want to. And let me write down the following. Sigma times sigma is equal to 1 plus psi. And let's understand what this means, because we'll do category theory next lecture, so this is important. What this means is that if I take two vortices, or two Majorana fermions, bring them together, they can, of course, hybridize, and then there's two channels in which they can hybridize. They can either go in a channel of even fermion parity or odd fermion parity. Okay? As we discussed in the first. Is that absolutely clear?
It means that I can make an electron of the tip.
It means that depending on the size of the coupling, I can what do you say? I can go back to the vacuum, or I can make a Bogoliubov quasi-particle. Okay? But is this clear?
I still don't understand.
Yeah.
So we said if we
Yeah.
put one plus, then I change from odd to even. Then I inserted one more, I will expect that we go back to odd again.
You go back to odd.
I will not have a state at zero energy, right?
Not on the edge. On the edge, there'll be no state. So the way it goes is you add one vortex. You didn't have any zero energy state without the vortex. You change boundary conditions from periodic to from antiperiodic to periodic. Now you got a zero energy state here. You run into trouble. Hilbert space must be even dimensional. So you must have another state, zero mode, at the vortex. Now I add another vortex in. So now I take this sample, make it the size of the universe, send this into the Andromeda galaxy. I bring another vortex in the Milky Way. This vortex can't know what happens. Can't know that I brought another vortex in.
But your
Physics
knows
local.
about the changes in the number of vortices inside. Isn't that
That's right.
As non-local as
That's right.
about two vortices?
Well, no. The point is the edge knows by looking at the momentum, at the periodic or antiperiodic boundary conditions. What I'm saying is that if I have a vortex, if I have a zero mode here, to move this zero mode away from zero, I'm going to need some sort of a Hamiltonian, right? Some sort of splitting energy term. Now, if interactions are local, there's no way something at long distance can actually split this, right? Because it's far away. So the edge knows because you're just putting a flux through the system, right? It's like Aronov bomb, right? Okay, so back to your question. So now you add another vortex in. Okay, this changes back to antiperiodic. You have no zero mode here, but you have a zero mode on this vortex, which is far away. So if I have no zero mode on this one, I'm still stuck with odd fermion number, odd number of states. So then I add one more. Basically, every time you pull in a vortex, you add another. You trap another state. Okay, so I'm going to call vortices sigma, and now I'm going to say sigma times sigma is equal to 1 plus psi. What does this mean? I really don't want you to think of them as bringing them together and annihilate them, although you can, and that's fine. I want you to think of them as basically two vortices. The fact that I have a Majorana mode in each vortex doesn't specify the full state of the system. Why? Because if I bring those Majoranas together, I have two channels in which they can go. Okay? And those channels depend on the microscopic of the system. For example, if there's T gamma 1 is 1 sigma, gamma 2 is, okay? If this is the Hamiltonian, then this is, if I make gamma 1 plus I gamma 2 to be the complex fermion, then this is C dagger C minus 1/2 T. So depending on this T, okay, they can go either into an odd fermion number or an even fermion number in terms of this C. Okay? But this C is just kind of a construction, it's a non-local operator if they're far away. So it's really just telling you that two Majoranas can go into two channels of different fermion parity. Okay? So the way I want you to think of this diagrammatic description is, this this rule is that when they're far away, okay, even though these states Hamiltonian-wise are at zero energy, so they're like, there's no splitting, because if I surround this thing and by like some, if I kind of like surround and make an experiment in the whole system, just telling me that there's two Majorana here doesn't specify the state of the system. I need to know the state in which they are when they fuse. Okay? So that's why the states of this system are, for example, specified by, we're going to call them psi, sigma, sigma, fusing into 1, or think of them as some states, psi, sigma, sigma, fusing into psi. Psi is a fermion, 1 is the vacuum, this is the BDG vacuum. Okay? This is the BDG quasi-particle, or some dressed combination of them. And when I add two Majoranas, they can either go into one or the other. So basically, the new thing that we found is that with these Majorana fermions, you don't have just one channel to go to; you have two channels to go to. And this is the hallmark of non-abelian. Well, this basically will imply non-abelian statistics. So every time you've got a fusion rule, so this is called fusion rule. And in general, we're going to learn in the next lecture, you can have...
Because of the two possible parities that we put together?
That's right. So these two are different sectors, because they have different parity. They don't talk to each other.
So basically in any system that I could fuse two quasi-particles to form a fermion, I could take two particles, I could get non-abelian statistics.
Well, it's more than that. These need to be... So this happens always on a zero energy manifold. Okay? So these are zero modes, and they're... yeah. Okay. So
why would I not know what T is?
Well, because it depends on the microscopics. If I've got like some, in general, the way you do this is you've got your system, and then you excite Majoranas out of it. So say your system is in some state. You prepare your system in some state. So I prepare it in state 1. Say I have my experimental wonder, and I prepare in state 1, and now I excite two Majoranas out of it. That's going to be described by this state. This is kind of like a, then, or I can add an electron to it, and then it's going to describe by this state. But those are two distinct states that don't talk to each other. Okay? Okay. All right. So now let's find out some more fusion rules for this theory. Of course, everything, so this is the condensate, this is the BDG condensate. Everything that fuses with the condensate fuses to itself. Because the condensate is just inert. Okay? And the last fusion rule that I have to find, so this basically is like kind of an axiomatic way of what happens when I strip out all the microscopic details out of the problem. Okay? So the last rule I have to know what happens when I add this fermion to this. Okay? And we can find out actually what happens by some consistency that I can show you in the next lecture. But basically, some associativity there's some ruling category theory that will tell you. But the point is, like, it's very simple to understand what happens. If I bring a Bogoliubov quasi-particle, or if I bring a complex fermion next to a Majorana, there's going to be a 3 by 3 matrix. I'm coupling between them. 2 of them are going to split. I'm going to get another Majorana by default. And all Majoranas are treated equal in this kind of axiomatic way. So this is kind of the if you see this, if somebody tells you I've got a theory that looks like this, you'll immediately understand that it describes vortices in a superconductor. So this is called Ising fusion rules. And we'll learn how to describe them better next. Okay? Yeah.
Just what does the two sign
Just what is what?
Two?
So they can. So two fermions can go back into the vacuum, right? Because the vacuum is a condensate of fermions. Yeah. Okay. All right.
Can I
Yeah.
try to rephrase what you said there? So when I generate the two Majoranas or the two Majoranas, I cannot know precisely at that point or at that area the parity, and this is why I don't know which of the two I have. So then I have to consider sort of both.
Well, if you prepare your state, if you've got if you can measure, if I've got a sample and I can tell you the fermion parity in that sample, for example, okay, and I create two Majoranas, then I know where they sit. I know that they sit in this state. Okay. Okay. But the point is, but that's making a pure state. The point is that there are two choices that I can prepare my sample in and then get two different states. Mm-hmm. So for example, if I took two of these, which fuse into this channel, this one, and brought them together, I'd get different density than if I brought these and they were in this channel. If I measure something, right? And you'll see that, so basically this is tantamount to non-abelian. It's called non-abelian fusion rules, but it's the same thing as non-abelian statistics when you've got more than one thing here. Okay? And that we'll see next time. Well, in the next two lectures. All right. So just keep this in mind. So now what I want to do, so we found out that it's got a classification on the edge, which is Z, a classification of defects in the bulk, which is Z2. And when it's odd, when the Chern number is odd only, that's when you have Majoranas. You've got the fusion rules that look like this. And now I want to look at what the classification is in the bulk of the sample, right? So none of these really has an unperturbed bulk, right? Because I have here an edge and here I have a defect and I'm just looking on the defect. So now I'm just trying to understand what the classification is in the bulk of the sample. So no edge. And here I claim that there's a 16-fold classification, which we'll learn how to, I'm not going to, so all this is explained, not these arguments, but this, how to get from category theory, from this thing you can get to 16-fold. Well, this is half of the 16-fold way. This is just the odd Chern number. So you can get 8 states. So I'm not going to explain how to do it in category theory through F moves, but I'm explaining how to do it in a much simpler way through the S matrix, hopefully in 2. Because that's, but now I want to just give you a flavor that the classification, the bulk, has got something to do with number 16. And each of that 16 breaks up into 2 sectors when Chern number is odd and Chern number is even. So let's just see. So if I look in the bulk, so I make a bulk which is infinite, no edge. And now I create vortices. And since I don't have an edge, I got to create 2 vortices at minimum. And what I'm going to ask, these vortices might or might not have some particles on them. I don't care. But really, the only thing that can characterize the state in the bulk is I'm not looking at Hamiltonians anymore. These are zero-dimensional, these are like zero-energy sectors, right? I'm looking at the zero-energy sector. So the only thing that can characterize a state in the bulk is phases that are acquired upon braiding things, upon taking things around one another. Okay? Please ask questions, because, it's good. It's cathartic. So So what I'm going to ask is what happens when you not take everything by 2 pi, but exchange particles. So just take everything by pi, say, and exchange and move. So you really do this and then move. You can do that, right? Why? Well, obviously, if I would be allowed only to do 2 pi rotations, then a fermion would do nothing. But, fermions have, when you exchange 2 of them, get a minus sign. So really we should look upon what phases you get upon exchange. Okay, so in a superconductor, this is a Majorana. This is a say it's a chiral superconductor. And I'm going to ask what happens when I take a vortex and move it around. What are the possible phases that my wave function upon switching? My wave function will get a phase, and what is that phase? Well, I can't tell you what that phase is for all the examples through the simple argument, but I can tell you that there's a 16-fold classification. So let's do it. So what I'm going to do is I'm going to use a lot of BS, and I'm going to first take this superconductor and make a model for it. Let's call these Majoranas A, J, A, K. So these are not the Majoranas in the vortex. They're the Majoranas in the superconductor. They're the constituent. I have in the superconductor I have electrons. I can break up those electrons to Majorana fermions, just like I did in the Kitaev model, right? These vortices, don't think of the Majorana in the core of the vortex. There's there could or there could not be a Majorana in the core of the vortex if the Chern number is odd or even. But here I haven't specified a Chern number. So this AJ are just the Majoranas in the superconductor, the ones that I break up the electron in just for my amusement. So take one such superconductor and now double it. So I'm going to take another one. So call this A1J. Let's call this A2J. I'm going to kind of double it. This is the first thing that I'm going to do. Okay. And now add these together to obtain a Hamiltonian. Okay. Where C is, so these J's represent sites in the 2-dimensional superconductor. C is AJ1 plus AJ2 over 2. Okay? So what I've done is I've taken 2 chiral superconductors, put them together. Why? Anybody has an idea? I mean, everybody has an idea, so just blur it out. Why would I do that? What do I want to create by putting 2 chiral superconductors together, just like I was putting 2 chiral Majoranas on the edge together? Quantum Hall effect. So this Hamiltonian is a quantum Hall effect, integer quantum Hall effect, with Chern number C. Okay? And it actually has some emergent SO2 symmetry that you can write down if you want. But I don't. Okay. So you must remember that I double my system. So every phase that I get is going to have to be divided by 2 because I've doubled my system. So I'm going to compute the phase of 2 vortices in an integer quantum Hall effect of Chern number C. Okay? So I have integer quantum Hall effect. So now I have charge symmetry in this new operator, FC dagger C. Okay? So by putting 2 superconductors together, I've restored some sort of, hypothetical charge symmetry that I did, it's a Gedanken experiment. So I have this integer quantum Hall effect. If I add flux 2 pi, which is in units of h over 2e, so it's really flux pi in units of e. Okay? So when I talk 2 pi, it's the superconductor, but it's really pi in units of h over e. What does it do when you thread flux through a quantum Hall state? I think either Nicolau or Joel pointed that out. You create, of what charge? So this flux I can thread it by making an electric field that goes like this around the flux, right? Yeah? But this is a quantum Hall state. So it's got a current. If I put an electric field like this, it's got a current like this. Yeah? There's the Hall conductors. So it will trap charge around the vortex. How much charge if it's got number C? Huh? I mean, they're both good answers, but I'm waiting for the third one. So yeah, how much charge will they trap? Come on, I want to do some other stuff too. C over 2. So 2 pi. 2 pi is like introducing a full flux. It'll trap, it's like basically the same thing. This is kind of the same geometry as the Laughlin gauge argument, which you thread flux. I mean, if I make this cone and, make this larger and deform the system, I'm just threading flux. So if I have C chiral modes, I can make this vortex larger. I have C chiral modes, and these if I thread flux 2 pi, I'll trap charge C, but if I select flux pi, I'll trap charge C over 2. Yeah? Is that absolutely clear?
No, could you repeat this?
So, yeah. So, in a quantum Hall state, if you thread flux through it, that's the same thing as basically making as basically having an electric field, right? Okay, if you've got an electric field, then you've got a Hall current. Okay, so let's see what happens when let's say I make this vortex larger, okay, and wrap these around, make 2 vortices. Okay, so this is the same geometry as having this. Okay, because I can make this vortex larger. And that's going to bring, I can then blow it up like this, and the other vortex I can, okay? So I'm just going to focus on what happens on this vortex. Now threading, making this vortex is the same thing as putting an electric field here, like this. So it's the same thing as putting an electric field like this here, threading a vortex like this. Yeah? So now, as a function of this momentum here, the spectrum looks like this. I've got 1 edge mode, 2 edge modes, whatever. 3 edge modes, whatever. Right? As I thread flux from 0 to 2 pi, so I have some Fermi level in my system. These are occupied, these things. As I thread flux 2 pi, what happens is that the momentum here, you're basically changing the momentum from what it is to 2 pi over L. So you're changing the momentum from here to here. So you're basically moving all these particles up. So then you're left, after threading flux 2 pi, with a situation where you've got C charges accumulated here that came from here. Okay? So if I thread flux pi, I have C over 2. That's not entirely correct, but that's why I said this is slightly a BS argument. So but it gets the. I mean, I'm gonna show you that there's a Z16 classification through rigorous category theory, but 2 next lectures. But so far, let's just accept this argument. So, but are you happy with that argument? Well, happier.
In fact, the problem was the end. Why we could go to C over 2 when it's 75.
Sorry, I can't hear you.
The fact that we have C when we have 2 pi
Yeah.
was okay. The problem was also goes from.
Oh, okay, that was the problem. Yeah, that's don't worry about that. Okay. Yeah. Yes.
Why are you using h over p units and not h over 2e? Because I would say you want to h over 2e.
So the flux is 2 pi in h over 2e. But in this case, the charge of this is e. Okay? So I'm just using in the units of the charge of this guy. All right. So now I've trapped a charge C over 2 here. Okay? So now I'm going to ask what happens when I take this charge and move it around this vortex. This vortex is also a pi vortex. Okay? So what around a Bohm phase do you get when you take a charge and move it around a vortex? What's the phase? No, seriously, what's the phase? Huh? What's S? I only have C. If by S you mean if S is equal to C, then I still don't agree. But so so just bear with me seriously. We've got like 10 more minutes, so I know everybody's tired and. So it's a vortex pi, and I take this C over 2 around it. What phase will I get? Pi C over 2, and that's if I take it all the way around it. But if I just exchange it, what will I get? Okay? And that's for the quantum Hall effect, but that's 2 exact copies of this Majorana, of this P plus IP superconductor. So roughly the phase I will get for the initial Majorana system is e to the I2 pi C over 8. Half of that. Well, square root of that, not half of that. Which is e to the I2 pi C over 16. Okay? So that basically shows you that the bulk classification is Z16. Well, it's not really Z16, but it's more complicated. 16-fold. Right? Because I can't distinguish phases. The only thing I can measure in the bulk is phases, if I don't have an edge. And I can't distinguish phases between C and C plus 16. You agree? Okay.
Why is looking at 2 vortices enough? Isn't it 4 or 5?
Well, if they're abelian, so if C is even, that won't matter. They'll just add up, basically. I mean, roughly. If they're non-abelian, it will matter. But you can still show... So here I've just computed like just basically an abelian phase. I didn't care about very much. So indeed, this classification actually breaks up whether C is even or C is odd. And there are 8 phases in C even and 8 phases in C odd. Now, it has to be that way because well, I don't know if I'll get to show that, but basically a topological quantum field theory in the bulk is only sensitive to the central charge. The central charge is the same thing as the Chern numbers, number of edge modes, chiral edge modes that you have. It's only sensitive to that mod 8. So if I had mod 16, that would be not correct. But indeed, this actually breaks up into 2 theories because if it's C odd, this is non-abelian because I've got Majoranas. But if it's C even, it's abelian. So they're completely different theories, and actually even those break further down, but I won't get into that. Okay. So does that questions?
Is this C related to the central charge in the usual CT sense?
So yeah. So
in the bulk especially. Bulk does not
there. I mean, yeah. No, there is no conformal symmetry in the bulk. You don't. Even on the edge, the spectrum is not always linear. So as a if you were to derive it from microscopics, is not entirely kosher to do. That's why, for example, well, there's two different answers to this. On the edge, you can actually prove that even if you don't have linear spectrum, the thermal Hall, so just take a mode that doesn't have a linear spectrum. Any energy, as long as it's chiral, I can prove that my thermal Hall conductance, which is related to the central charge, is. What's that? No. So that's no. I can prove. just derive the thermal current. You can just do a continuity equation, derive the thermal current. I can actually do it next time. And no matter what, if you've got a chiral mode, you're going to get CT squared over 12.
But what is C without conformal?
That's a good question. And you don't have conformal symmetry in the bulk, but you argue that that's kind of a in my view that's kind of something that's still remaining. Whereas the fact that you can write down conformal quantum Hall wave functions as correlated with conformal field theory, those are just observations.
Yes.
But basically, the point is we have all this machinery and the things match. So it's not clear whether there's no conformal symmetry in the bulk, obviously. So, that's kind of a deeper question that I don't have the answer to. Okay. So now, last thing I want to do is before. So these two lectures. Yeah. Hi.
So this is a good classification for the superconducting class.
Yeah.
So the same argument if you were to apply it to the quantum effect directly. You went as you used the quantum effect to derive the proportionality, but if you don't focus on the quantum effect.
No, because this thing. So if you do it in category theory, which I'm going to show you next time. Unfortunately, I won't do it for. I'll do it for Fibonacci because it's easier. If I'm to do the F symbols for this, I'll go. Well, we all will go nuts. But basically, the answer to the question is the following: if you try to do it in axiomatic DQFT, you have to have some fusion rules. So you define. So basically, the fusion rules that I had before define everything. And that's not really transparent. So in Kitaev's paper, the 16-fold way, that's not really transparent. He actually puts in, for example, that psi is a fermion. He puts in that the spin of psi is 1/2. You don't need to do that. You get that out of the theory. So basically, just the fusion rules of this damn thing define everything. And the fact that I've got fusion rules here, these fusion rules that people write down here are specific for a superconductor. In the sense that, if I have quantum Hall, I can have a charge and in this case, things go back to the condensate, to the one. So, yeah. So in effect, writing down fermionic theories is kind of hard in this case. So writing down even, Laughlin states, fermionic Laughlin states is very hard because you have to identify the vacuum we always identify the electron with a vacuum, or the boson with a vacuum. And while that's fine for a boson because it doesn't have exchange statistics, the fermion is not fine because, so you can't build modular theories in most cases that have a fermion in them in the quantum Hall effect, for example. So I'll explain this maybe in the last lecture. Okay. But basically the answer to your question is it's in the fusion rules. And those determine everything, as I'll show. Okay, so non-abelian statistics. So I'm going back to C odd. Okay, and let me see, did I have anything else to know? Okay, so I'm going back to C odd, and I'm going to take vortices. I'm going to make 4 of them. And the reason why I'm going to make 4 of them is the following. How many complex fermion states would I have out of two vortices? Come on, just power through 5 more minutes. 2. But those are they're not split, but they have a fermion parity, right? So I can split them by a quantum number, by fermion parity. That's not good, because if I want anything non-abelian, I want to have like a degenerate set of eigenstates that I can rotate in. How many states will I get from 4 vortices? 4. How many have even parity?
2.
How many? Okay. So 2 of okay. So I'm just going to create 4 vortices and have these Majoranas: gamma 1, gamma 2, gamma 3, gamma 4. All right. So then what I'm going to do is I'm going to create, you can prepare your state so that you create these out of vacuum. Okay, so I just kind of like somehow I'm able to like tune my microscopic, so I create those out of the vacuum. In that case, it makes sense, but of course this is the statement that I'm going to make now is basis independent, but it makes sense to write down a complex fermion, gamma 1 plus I gamma 2, over 2, gamma 3 plus I gamma 4 over 2. And the set of states are I actually call these A and B. So our set of states are 0, 0, and so I'm going to label states by occupation number of this. 0, 0, 1, 0, 1, 1. These are even fermion parity, and 0, 1. These are odd fermion parity in this fermion, whatever this is. Okay. So now I'm going to ask what happens once I take, first of all, once I exchange this with this. So once I do this. And then I'm going to ask what happens once I exchange this with this. Well, not exchange, but actually take it around. Okay? So let's see what happens. So what happens, first of all, the fundamental thing is what happens when you exchange two. So, and this is again a bit, these arguments appeared in literature, but they're not solid proof in the sense that you need to compute other things. So they're just arguments again. So axiomatically we'll show this in 2 lectures, but even that's not a proof because you don't know that your system, your real system, is what this axiomatic thing will give you. Okay, so let's see. So I've got a vortex here and another vortex here. So gamma 1, gamma. I'm just focusing on these two, just to see what happens when I take one around the other. So I'm going to take one here. I take not one around the other when I switch them. So I switch them. So now remember that each of these vortices, when you go around them, the phase winds by 2 pi. The phase of the superconducting order parameter winds by 2 pi. But that's not a trivial winding. As I said, these vortices have a branch cut, a line that's gauge dependent, that tells you where the order parameter winds. And we're going to pick a point at which the phase is not multi-valued, just goes at infinity. Okay? So each of these two vortices have a line around which the order parameter winds by 2 pi. Now if I take one vortex and cross that line, that's like doing what Felix did with the e to the I phi over 2, phi being the phase of the superconducting order parameter. So normally, if you take gamma 1 into gamma 2 and gamma 2 into gamma 1, normally this would be the case if you didn't have a superconductor, if I just took things into each other. But since I have a superconductor, once this crosses this, and wherever you put these lines, they have to cross. One has to cross. It's always an odd number of crossings. However, I can make this going like this a bit, crazy, but there's always an odd number of crosses. Whenever this crosses this, you get a minus sign. And this is the fundamental thing that happens when I take one and get into the other, and when I switch them. So, I can represent this by an operator. I can represent this by an operator tau 1, 2, whose matrix representation so I have tau 1, 2, gamma 1, tau 1, 2. So this is 1 plus gamma 1, gamma 2 times something, times, what is it? Well, times something, forget about it. It's times 1 over square root of 2. Okay? So you can do this and find out that this is just gamma 2. And gamma tau 1, 2, gamma 1, gamma 2, tau 1, 2 is gamma 1 with a minus sign. Okay? More generically, if I want to switch any vortex, it's obvious how to generalize this operator. Tau ij is e to the I pi over 4, gamma I, gamma j. And this is a property that whenever whenever I acted on I and j, it leaves I, it sends I to j and sends j to minus I. And if I acted on k, which is not I nor j, it's invariant, because obviously it's the quadratic operator. So if I acted on k, it's just going to anti-commute twice, leave it invariant. Okay? So now all you have to do is compute. So this is what it happens upon exchange. So now what I want to do is I want to, in this system, where I define my basis states. So I take these two Majorana's out of vacuum, these two out of vacuum, and now I want to, instead of switching these two, I want to take this around this, or switch these two, or you can switch just these two. So I want to do something non-trivial, switch this with this, basically. Okay?
Is that what we're going to do next class?
I started at 4:34. 35. This is what I'm just finishing, just right now. I'm almost done. So all you have to do is compute the operator tau 2, 3 in the basis of these states. Okay? Just compute this in the basis of these states. And see that, of course, it's going to be block diagonal in even and odd fermion number. Okay? But you will see that the matrix is not diagonal. So you compute tau 1, 2 in the basis of these states is going to be diagonal. Any other operator that's either tau 1, 2 or tau 3, 4 is going to be diagonal. You compute something that's in between these is off diagonal. It's got off diagonal elements. So that says that if I create these particles from the vacuum and move them around, then I mix these states. So if I create the particles in this state, okay, so I have a set of degenerate states, 1, 0, and 0, 1. I kind of initialize my state in 1, 0. Switch 2 and 3, then I get a combination of 0, 1. I get 1, 0 plus I, 0, 1. Okay? And this is a simple thing. I can just take this operator, gamma 2, gamma 3, compute it. I can, compute it in the basis, because gamma 1 is A plus A dagger. Okay, and gamma 3 is B plus B dagger, etc. So you can just compute it in the basis of the states and find out that it's off diagonal. And that's related, as we'll show, to the fact that you've got a non-abelian fusion rule. Okay, so let's take some questions. Really? Yeah.
You see, this is diagonal. So how can you start from 1, 0, for example, and get a mix of 1, 0 and 0, 1?
So these are degenerate states, right? So these are degenerate states. If you've got just one state in your system, then you can only get a phase. But if you've got degenerate states, there's nothing that, the most general transformation that you can have is a matrix. And this is what happens here. Okay? And this is this is the basis of non-abelian braiding. You can just see that you build them, you build this basis. If I, for example, build the Majorana fermions out of 1, 3, the complex fermions out of 1, 3 and 2, 4, then, if I build them out of 2, 3 and 1, 4, then doing 2 and 3 would not get me a non-abelian phase. But doing 2 and 4 would then. So there's always a non-abelian exchange matrix in this case. Okay, any other questions? Okay. Well, let's eat or do whatever you want to do.